everyone, and thank you for coming on this super hot day to the Rasa office. It's our 6th Deep Tech Meetup, which means that it's our 6th meetup where we get like tech people coming in, also hearing a speech of people who are researchers and like talking about different technologies we at Rasa, for example, use or our machine learning engineers are interested in. Today is actually quite a special day because actually one of our in-house researchers is going to give a speech. And he's going to talk about transformers, so I hope you have some questions prepared. Yeah, let's hear a round of applause for Vladimir.
Wait. Hi. Hi, yeah, my name is Vladimir. I'm a machine learning researcher here at Rasa, and we decided to make this talk about transformers, trying to explain what people already explained, and you probably read in many different blog posts, but I think it still makes sense to have a talk about it. Please keep in mind that this talk is very biased to my own complications that I had with understanding the transformers. So if I didn't explain something that you don't understand, maybe just shoot in a question. And please don't hesitate to interrupt me in any point if you don't understand something. So just a bit of a history why we decided to make this talk in the first place. Last year, we were playing with different architectures for our core system, which is the machine learning algorithm for the dialogue. And we found out that attention is actually something that some people in Google found out half a year before, that attention is actually more important than the LSTM. And back then, the transformer was a half a year old, and they took a look at this and I thought, no way I'm going to understand that. It's absolutely impossible. And I forgot about it, and then we released this paper on the embedding policy, which uses a lot, which relies on attention quite a lot. And that's basically was it. But then time passed, and this winter, we decided, well, there is no way of going back. Many people use, and BERT was released. And apparently transformers taken over the world. So I have to re-evaluate and like my knowledge about it and try to actually understand that. And funny enough, after looking at the code of the BERT implementation, I managed to understand that. So it's like I can recommend to check the Google's GitHub for BERT. It's, in my opinion, quite a clear TensorFlow implementation of transformer, much more clear than the tensor to tensor one, the one that the original from the paper. And that's when I understood that transformer is actually simpler, much simpler than it looks like from the outside. And that's why we decided to share my insights or our insights about the transformer, and hopefully you will also agree with me that it is actually a very simple thing and quite a beautiful thing. So, and in this talk, I will mostly concentrate on in my opinion, the most complicated part of the transformer is the chimera beast called multi-head attention. And we will step back from the OpenAI GPT or BERT and then just go back to the original transformer and try to figure it out what is multi-head attention, what are positional encodings, and so on and so on. But first, so according to I think from the intro, from the original paper, attention is all you need. The transformer is the model architecture that gets rid of the recurrent connections and totally relies on the attention over the time steps to model the time dependency. And attention is the word that is probably the most often in this paper. And so before we actually try to understand this attention mechanism in the transformer, let's go couple of years more back to the paper neural machine translation by jointly learning to align and translate. I don't know if it is the first paper that introduced attention, but I think according to general knowledge, it's considered to be the one that started this movement of attention over the world. And basically the idea is that if you have the encoder-decoder architecture, the fixed size encoding vector that is output of the encoder is not enough to capture the meaning of the arbitrary long sentence. And so what is the encoder-decoder? The classical encoder-decoder is you have the input sentences, you have some kind of RNN or maybe multi-layer RNN that outputs the last encoder vector, it's a fixed size vector, and then the decoder, it's another set of, it also could be multi-layer RNN. It uses this fixed size encoder as an input to the first step, and then produces token used as an input to the second step, and produces the second token, and so on and so on and so on. And the idea is that this fixed size vector cannot catch the arbitrary long input sentence, all the meanings that's possible. So the idea is to somehow, and also in general, when we try to translate from one language to another, we don't care for the whole language actually. We just usually look at certain words or combination of words in different parts and translate like that. So the idea is that there is some kind of, so for each time step of the decoder, there is some kind of a context that is somehow hidden in the encoder, and it is different for each time step. So the question is, how do we calculate this context? And so let's phrase the agreement on the European Economic Area was signed in August 1992, and we want to translate it into French. And we want so far the accord, the agreement, sur, which is, I think Google Translate told me that is on. And what we want is basically, we only care for what is here. And it's kind of represented here by this thick line. Unfortunately, you cannot see, but there is another very, very thin line over all the other steps. But the important thing is this thick line that's like pays attention only to this on and outputs the French token sur. And so let's introduce a couple of notations. So we will name the Hj is the state, internal state of the encoder. J is the time of the encoder. And then the Si is the state of the decoder. And I is the time of the decoder. So how do we calculate this context? So for the time step I of the decoder, we can create a constant vector Ci, which is basically a weighted average over the all possible encoder state Hj, with some weights alpha ij, which are called attention weights or alignments. And that's basically it. So the only thing that we need now is to figure out how to calculate these alignments for the time step I of the encoder. And these alignments, well, I guess all know that. It's just basically a softmax of some score between the previous encoder input Si minus 1, decoder input Si minus 1 and the all possible encoder states at J. And score, probably there are much more different scores, but there is two most popular scores. In TensorFlow library, they are called Badanao score. It is the original one from the paper, jointly align and translate. It's a tanh of the sum. And long score, which is a dot product score, which with some weighted matrix. And these WM, WQ, WM, they are learned weights, and also this V. They are learned weights. So basically, you create additional network that scores the input for the current state time, Si minus 1, with all possible encoder outputs, Aj, and take the softmax over them, and then basically creating the probability distribution and create a soft sum to basically pick the one encoder or like maybe several encoder states that are important for the current time decoding. And that's basically it. And for example, for the whole sentences, that's how it all looks like. So In the beginning, it's very straightforward. But when we need to translate European Economic Area into zona, I don't speak French, sorry. But the idea is that zone is area, so we need to actually, so at the point we arrive here at European, it's not the zone, so we need to pay attention to area. For economic, we still pay attention for economic, and for European, we pay attention for European, and so on and so on. And sometimes we need to, as we can see, both of them, because probably the was signed is kind of like together, and we need to pay attention to several ones in order to predict these tokens there. And the rest are relatively linear. And because it's softmax, you can see also some weak connections over there, but that's inevitable. But that's basically the whole idea of the attention between encoder and decoder. And now before we move to transformer, do you have any questions so far about the attention encoder-decoder? Great. Now let's go back to the transformer. And this is the pictorial scheme of this part is the encoder, this part is the decoder, and that's basically it. I will concentrate now on the encoder part here. And let's see, it contains several things. So input embeddings, I think, is fairly straightforward thing. Positional encoding, something new. Multi-head attention, also something unknown. Addition and normalization, hopefully you all know. Feed-forward neural network, also well-known thing. And again, addition and normalization. So there is basically two main things that are tricky and were introduced in this paper is the positional encoding and the multi-head attention. And now let's take a look at the attention first. So what is that and how does it relate to the old one? Because here at this point there is no encoder-decoder. It's just only encoder. And that's the equation from the paper. Some symbols, QKV, softmax over QKV. So softmax is something we saw before, right? The rest we never saw before. So, and they call the keys and V and values. What are they? I read it several times. I didn't find the explanation. So, but we can go back and take a look at our encoder-decoder attention. Let's see what we have here. We have some context that is a soft sum over H, and we can assume that H are values because we need the values to sum over them. And then they say that they use dot product, so the idea is long attention. And looking from this QK, so the input to the current time for the decoder is I, that should be a query, and this H should be a key again. And if we go back to the implementation, then we can actually see that indeed key and value are processed of the H of the encoder state, and WV and WK they are learned weights, and query is the processed S, but in case of the transformer, because it is self-attention, S is equal H. Self-attention means that just S is equal H. So you take the same vector at each time step and you calculate attention with itself at all time steps. And all of these weights, they can be learned. And as a result, our query is the tensors of shape Beige, length. In this example, length is 10. It's the sequence length. And channels. And channels are 8. And so basically, I only picture here length and channels, but you can imagine additional dimension of Beige. So this is for Beige 1, say. Yes.
So is 10 the length of the sequence? Is this a window, or is it just?
No, it is the length of the sequence. So it's just for this example. It is like usually 256 like or millions or whatever.
But is this the variable length of the sequence?
So in general, when you have a sequence modeling, you usually pad your variable length sequences to some fixed length. For example, you pick the sequence that has the maximum length in your data set, and you pad with zeros all the other data sets.
Okay, so it's padded to the maximum.
Yeah, padded to the maximum, or padded to some fixed one. It depends. So in transform, and it depends on the architecture. Sometimes they just cut the long sequences and pad it like to the fixed size sequences. Yeah.
What are channels and why do you have 8 of them?
Yeah, channels. Channels. Yeah. So length is the sequence length, and channels is the hidden transformer. 8 is just because on the picture that I found it is 8. It's just an example. Usually it's like 256, 512. Name your number, depending on your GPU, TPU, or anything. They call channels is in a normal sense just number of hidden units of your feed-forward neural network. Next? No, come on. Yep. Is it next? Yep. And so what's going on behind this equation? So like dividing by square root of dk is a dimension of the channels. It's like in this case it will be 8. So square root of 8. But it's not very important. So the question is like, what is this qk transpose? Qk transpose is the score, basically. The one that we had before. And how it works is, so if you have imagine we have only one batch, then you have a query, say sequence 10 and then 8 channels. You transpose the keys, then you multiply it and you get the attention weights matrix that is length by length size, and like batch length by length. And that's your attention weights. So in the example above, it was also alpha ij. So this is alpha ij. So this is the before encoder time, and this is the decoder time in this sense. And then you take a softmax of it, like this, and then you can multiply it by another tensor of shape batch length channels, which are values, and you get the output which is of shape batch length channels. And each row corresponds to the current time of the decoding time here. And then this is the new context for each time step. There is a couple of things that is important to keep in mind, that all time steps are processed simultaneously now, meaning that all time, like when we calculate the attention, when we calculate this attention weights matrix, we have all access to all the values. So we have the access to the future as well. For the encoder, it means that by default encoder is bidirectional because it can see both sides. And for decoder, it's actually something that is harmful because during train time, we actually see all the future steps. But during the test time, we only see up to here because we decode one by one. And for that, and this can be solved by simply applying the masking to the attention weights. And like this. So basically, we mask out the upper triangle part of the attention weights so that we never pay attention to the future. And then when we multiply it by values, automatically, for each time step, the future values here will be masked out. In the default architecture, they do it in the decoder, because decoder shouldn't be allowed to see the future during training. But also, we can do it in the encoder to make to mimic the unidirectional encoder. Then each time step, it only sees the previous input, which is quite important. For example, if you want to apply attention for the dialogue. Because during training, again, you see the whole dialogue, but during testing, you only see up to current time. And that's basically it with the attention. Nothing super complicated. Another thing is, okay, what is multi-head? Multi-head is another interesting idea that, so before so again, this is channels or number of hidden units. Before, in the encoder-decoder setting, we would calculate one attention over all the different units, and this weight matrices in the keys and queries and values will be the same for the channels. The idea is to split these channels to different heads. So basically, if we have if, for example, we have 16 channels and number of heads is 4, then the first 4 units will have their own set of weights, the second 4 units own set of weights, and so on and so on. So that it actually can learn different attentions depending on the channels and combine it differently. So how it is done is basically if you get these query keys and values as a tensor of shape batch length channels, you divide channels by the number of heads, and you transpose the vectors to have batch number of heads length, and then channels divided by number of heads. It's just simple transpose, and then when you multiply everything, effectively, your channels will become independent, and your weights will also become independent for creating the context vector, the output vector of attention. You transpose it back by concatenating these heads back together to create these 16 channels back, and this will be the input to the next layer of the transformer. And that's basically what multi-head is. The idea is to split, to have, for different channels, have ability to learn different attention to different time steps. That's it about the multi-head attention. Do you have any questions? Yep, I cannot see you.
Difference in how you split these channels?
What do you mean?
I mean, the channels are the dimensions.
Yes.
If you, for example, take heads random dimensions.
There is no actual difference because you randomly initialized weights initially, right? And random splitting of heads is random perturbation of your channels. Of your hidden units. But since hidden units, they in one layer they're independent, you can randomly perturb them. Yeah.
Yeah. Why do we need like that early in the processing already attention? Because I mean, the LSTMs we use attention kind of to see something which is like way back in the processing, right? To get it back into the future. But there we just started actually.
Yeah, we just started with that because we completely cut it the recurrent connection. Because now the processed time step, they're completely independent. The token doesn't know about anything around it. And we need to reintroduce it somehow back, the ability for parallel computation. So LSTM doesn't really allow parallelization because you need to calculate one by now. But here, the powerfulness of this is that it is computationally can be very efficient because you process all time steps simultaneously. But then you need somehow to reintroduce the time dependency back. And that's another thing, that so far, this multi-head attention is what we called content-based attention. Is we pay attention to what is inside the time step, but we don't know when it was. So when you reshuffle it, it will be the same. It doesn't matter. It doesn't know this dependency. And that's what they propose to beat with what they call a positional encoding. There are two different types of positional encoding. One is just creating a random vector for each time step and fix it or learn it, for example, and then use it as an encoding for the position. But it has some drawbacks. Now anymore, your length cannot be variable sequence because you are fixed. So as soon as your test length is longer than your training length, you don't have the learn embeddings for the future time steps. So another way to try to combine it is to add some time varying functions to different time steps. The propose is to, come on, you can do that. Yep. Is to add sines and cosines for different channels with different frequency. So we have our 16 channels here, or number of hidden units, and then this is the length dimension. And so what we do is we split them by half. The first half gets sine, and the second half gets cosine. And then the first channel gets high frequency, And then the frequency becomes smaller until it is actually nearly constant. And that's regulated by not in terms of frequencies, but in terms of min-max time scales. It's a bit more complicated in the paper. I assume that mean time scale is 1, and then t is in this case will be the max time scale, and the idea is just basically that the value is the position position in time in your length, divided by the time scale in the power of the channel, where E is the basically number of channels and D is the number of channels in your essentially basically half. Did I have a slide? Okay, sorry. Yeah, and that's how it looks like. So we only take the first half, the d equal 8 of our for the rest you can imagine it's similar because it's just basically it starts from here because it becomes cosine. Essentially the same thing. So the first channel is the blue one. It's a very frequent sine. The second channel is the orange one. It's slightly less frequent sine. And then the green channel is, imagine, like very low frequency and then lower and lower until it's like, for the 8th channel, it's just basically doesn't change anything. So it's kind of time independent. And that's the idea. You just add these numbers to the embeddings for each time step. And for each time step, like you pick the number according to this graph and then according to this channel. Yes?
When you say add, do you mean add or multiply?
Literally add. Yes. So it's here. Add. And that's it. That's basically it. And then, so you get the embeddings of your input. You add the sines and cosines. You calculate the attention over your time steps. Maybe you mask it if you want it to be unidirectional. You apply layer normalization. Then you perform the feed-forward neural network on top for each layer. And importantly, again, this feed-forward neural network is applied independently in parallel to each time step, and they share weights between time step.
Why do you use periodic functions and not random functions?
So they use random functions, but random functions has a problem. So if during training you have some fixed some maximum length, you don't have random function for the further if your test is longer.
Okay, but you could make another systematic family of functions.
Yeah, you can have. Yeah.
All periodic, right? But you chose periodic periodic functions.
They just the usual the intuition. Yes, sorry, yeah, I forgot it. The intuition that if you have sine and cosine, and remember the score is multiplicative score. When you multiply sines together, it is you can trigonometrically it is equivalent to the sine of the sum or differences between the inputs. Like sum of x plus y, sine of x plus y is sine x cosine y plus cosine x sine y. So and then immediately vice versa. So you multiply your sines, and in reality you get sums of the times. So the intuition is that then it can learn the time differences between time steps. That's the intuition. In my experiments it doesn't work. But that's yeah, and that's from their blog. So that's the idea. In parallel, you create all feed forward. You recalculate the weights. This is was encoding state, and now you start decoding. You collect all the attention from the encoder. Then you collect the attention from the previous time step and encoder. Then again, the next token, attention from previous time steps, attention from previous time steps. Too fast. Sorry, I cannot talk too fast. So fast, and so on. So decoder during this is the test time. Decoder during test time is sequential. Of course, we cannot make it parallel because we don't know the future. But the encoder is and this is the bidirectional encoder without the masking. And that's basically it. Thank you.
questions? Wait, I just got up. Do you have more questions? Otherwise, Lucy, do we have some more questions from the live stream people? Oh,
Yes.
yeah, how much better is it actually on your dialogue use case compared to LSTM?
So compared to this one, it is as good as this one, but this one I actually couldn't train it on my Mac. Transformer trains in, don't want to lie, I think 40 minutes.
Okay.
So it's just the fact that it is parallel, it makes it so damn faster. And you can increase the number of hidden layers, you can increase the complexity and so on. There is one more complication though again. It has troubles of learning the order in time. Attention is still content-based. But anything else works way faster. Big fan now.
40 minutes on what kind of data set?
On the paper bought from this paper. So it's like 150 stories or something. 200 stories. But it's stories, so it's like, it's sequences. And I think the maximum length is 40 or something like that, yeah. And the LSTM trained for like 6, 7, 8 hours, something like that. But it also has complicated attention, so.
Cool, then we can wrap it up. Thank you all once again. And yeah, make sure to stay around. There's some more drinks, pizza, and yeah, thank you for being here, guys.